All right, so now we're going to look at the first practice problem from Module 6. So first let's read the problem. We're told that electrical charge is added to a metal sphere with a radius of 0.2 meters until it has an electric potential of 10,000 volts, at which point a second identical metal sphere with no net charge is brought close until a spark jumps between them. After the spark, the electric potential of both spheres is equal, and the process takes 2.5 milliseconds. So let's sketch what we have. So in our initial state, we have one sphere which has some amount of charge on it such that its voltage is 10,000 volts. It has a radius of 0.2 meters, and we have a second identical sphere. So the radius is also 0.2 meters with a potential of 0, which means that it has no net charge. Then our final state, which happens 25 milliseconds later, we have the two now have the same potential. So because they have the same radius, I know that the potential is just going to split evenly between them. So the potential on this one is going to be 5,000 volts, and the potential on this one is going to be 5,000 volts. There we go. I also know that half of the charge is going to be transferred. So whatever this Q was, this will now have Q over 2. This will now have Q over 2. So that is my sketch. My charge diagram is going to look pretty similar. I have one sphere. I have the other sphere. Let's say that this one, let's keep our charges on the surface so we're accurate. Let's say this sphere has 1, 2, 3, 4, 5, 6, 7, 8 positives, and this one has nothing. So when they are brought close, there's going to be a spark where electrons are going to go from the one with lower potential to the one with higher potential. So here we're going to say electrons flow to the left. And this still has 3, 4, 5, 6, 7, 8. And at the end of that process, there will be 4 positive on this and 4 positive on that. So we can say that like 4 charges worth of electrons are flowing, whatever those charges represent. So my representation matches what I think will happen in terms of my sketch. The total charge will be positive and smaller than the initial charge on both of these, and charge is conserved. 4 of my charges worth of electrons went from the right sphere to the left sphere. And so the left sphere went from positive 8 charges to positive 4 charges. My right sphere went from 0 charges to positive 4 charges. So charge was conserved on my representation. That's good. So now what we want to do is we want to solve for the current, correct? So I want to solve for the initial Q and for the current. So for the initial charge, I know how to calculate. Help if I could spell. I know how to calculate the V on a metal sphere. So the potential on a metal sphere is K times the charge on the sphere divided by the radius of the sphere. So we can say that 10,000 volts is 9 times 10 to the 9th newtons meters squared per coulomb squared times Q divided by 0.2 meters. Plugging this into my calculator, I get 10,000 times 0.2 is 2,000. 2,000 divided by 9 times 10 to the 9th. So Q is equal to 10,000 volts times 0.2 meters divided by 9 times 10 to the 9th newtons meters squared per coulomb squared. And let's see what we get from this. This gives me 2.22 times 10 to the negative 7. Let's check out my units. Well, I know that a volt is a joule per coulomb, which is a Newton meter per coulomb. So I have Newton meter per coulomb times meter divided by Newton meter squared per coulomb squared. So these 2 meters cancel with that cancels with that, this coulomb cancels with one of those coulombs, and I'm left with 1 over coulombs, which is just coulombs. So I do end up with the unit that I expected, and that doesn't seem like an unreasonable charge to have, given the charges that we've seen before. So this number is looking okay to me. I'm okay with it for now. So now we want to find the current. Well, I know that I is the change in charge, the amount of charge that flows over how long it takes that charge to flow. I also know that half of the charge, the original charge, is being transferred. So the delta Q that I'm going to use is the 2.22 times 10 to the negative 7th coulombs divided by 2, or 1.11 times 10 to the negative 7th coulombs. So my current is delta Q over delta T is 1.11 times 10 to the negative 7th coulombs divided by 25 milliseconds, which is 0.025 seconds. And if I do this calculation, I get 1.11 e to the negative 7 divided by 0.025. The answer that I get is 4.44 times 10 to the negative 6 coulombs per seconds is an amp. So now that I have my answers, let's evaluate it. So I've already shown the units work out. I've seen that my charge has approximately the right magnitude. Based on the things that we've seen before. One thing that I haven't checked is that this charge transfer would give me half the potential that I started at. So I can check that. So I can check, is 1.11 times 10 to the negative 7 coulombs the right final charge on both spheres? I'm going to warn you that in about 30 seconds my oven is going to go off. So I apologize for the loud noise. So we can calculate this. What is the potential if the charge on the sphere, 9 times 10 to the 9th, and I'm not showing my units here because I'm just doing evaluation, I don't need to put everything into it, times 10 to the negative 7th, divided by 0.2, this should give me 50,000. Or, sorry, 5,000. And if it doesn't, then I have done something wrong calculating my charge. So 9 times 10 to the 9th times 1.11 times 10 to the negative 7th divided by 0.2 gets me 4995 volts, which is approximately the 5,000 volts that I expected. So notice I'm not plugging numbers back into my original equations. I'm using a new equation with a number that I haven't done before to verify it. And then the last thing that I can say is this current reasonable? And my answer to this would be, yeah, there's not a lot of charge moving, and it's not taking a lot of time, so I wouldn't expect too high of a current. Like, I wouldn't expect this to be able to stop my heart or to power a device which takes an entire amp. So I'd say, yeah, I would expect a small current. And in fact, I can do the order of magnitude right here just to make sure that there wasn't any calculation errors. I am dividing a number which is roughly 10 to the negative 7 by 0.025. So what order of magnitude do I expect my answer to come up with? This can catch if I plugged something into my calculator incorrectly. Well, this is basically (10 to the negative 7 divided by 2.5 times 10 to the negative 2. So the number I would expect is 1 over 2.5 times 10 to the negative 5th, because that's how powers work. And this number right here is a number that's less than 1. So I would expect my answer to be of the magnitude of 10 to the negative 6. And that is exactly what I get. So that gives me confidence in my answer. And I'm going to end that here before my oven goes off again. So thank you for watching.